Welcome back. This stage of the class, I would like to talk about the source transformation and what is the reason behind this technique, why we would like to do that. There is an understanding that at times I don't want to go inside the design, inside the box under the observation, whatever the circuit is going to be. This is a circuit. In this circuit, in this class, I have a bunch of independent sources, and I have a bunch of resistors. I have topology. I can do nodal mesh, whatever I like. But sometimes I'm not interested about what happens inside. I want to specifically see how it is responding to a specific load. This L stands for load, and you can imagine our L to be, for example, the input impedance of a DVD player. So just for an AC, for example, you have plugs on the walls, and you bring in your DVD or your TV, and you put that and you plug it in inside. You're loading the system. If you take a look at the back of these devices, usually you see that there is an input impedance noted as 50 ohm. If you go into the lab and you take a look at the function generators or power supplies or so, for example, you would see a 50 ohm is noted. 50 ohm is a very typical useful value, kind of a standard, and everybody is trying to have the input impedance of whatever device they have set as 50 ohm, because as we are going to discuss that later in Thevenin and Norton, it's going to provide the maximum power transfer to the design that you want to have. So the load, we would like to see how the load, why the load is going to be at the end of the 50 ohm, but before that, I have a load, a typical load. This load can be short, which means zero, and it could be infinity, which means open. This load is actually imposing itself on the design. Inside the design, I don't want to know the details. I simply want to know, for example, what is this voltage and what is this current. I'm going to call that VL and I. Let me give you another example everybody can easily connect to. For example, I'm the instructor of this class, and I'm trying to accommodate as many people in my class as I can, right? Now, each one of you are going to be a book of a life. You have work to do, outside work, part-time, full-time jobs to do. You have family to take care of. You have kids. You have your own agenda. This is you. Although at times, with your permission, and when you come and you talk to me, I get a bit of a glimpse as to what happens inside you. But generally, I would like you to succeed in my class. For example, I would like to have A+ out of you. So whether you are married or single, I want to have A+. I want your success in my class. This is what I would like to see. I want this system to be basically responding to my demand. The demand is do the homeworks, do the quizzes, come to the lab, do the lab tests individually, do the midterm, do the final. That's the load. This is the load we are actually imposing on you. Now, if I wanted to consider a simple design in my mind, suppose you have a voltage source. I'm going to call this E, and you have a resistor. I'm going to call this Rx, and this is one possible circuit. This can't be any simpler than this. The simplest form of this design could be a series combination of a voltage source and a resistor. And also another possibility that comes to my mind is going to be a resistor in parallel with basically a current source. Let me call this IY, let me call this EX. This is one topology, one voltage, one current, one behavior inside. This is another topology, basically perhaps a different voltage, a different current, and everything inside. This is my inside event. This is inside a box. This is possibly one of you who are going to be a married person, and this is going to be perhaps a single person. You can see that. Now here is me. I'm loading you with demands. This is RL, and this is plus minus VL, and I want to have success out of this entire scenario. So that's going to be RL again. I want VL and IL. Now the entire objective is this. The load is the same, and that would be me. You are different. Each one of you have their own responsibilities and obligations. From outside point of view, I want to have the same success. That's my objective. I want to make sure everybody understands the topic and moves on accordingly. If that's the case, there has to be a relationship between these two designs. I want to identify that relationship. So let's begin finding this, solving this, finding VLIL from this circuit, finding VLIL from this circuit. Obviously VLs have to be the same, ILs have to be the same, and that's how I'm going to say these two circuits are behaving the same at the presence of the demands. So let's take a look at VL. VL is going to be, it's the voltage divider. It's going to be RL divided by RL plus RX times EX. How much is IL over there? IL is obviously going to be EX divided by the total resistance I'm going to see. You can also say that IL is equal to VL divided by RL. If you divide VL by RL, RL is gone and it's left. Ohm law. VL is equal to RL IL. Let's take a look at the second design and see how it is. IL is easy to find. IL, you can actually apply the current divider principle. I'm going to use a different color. So IL is equal to, let's do the Ohm law, the G rule, 1 over RL plus 1 over RY times IY. Let's simplify this because I need that. So let's do the common denominator. 1 over RL, RY, RL plus RY times IY. Now RL and RL is gone, RY comes on top. RY divided by RL plus RY times IY. That's IL. Let me double check to make sure everything is fine. This comes on top, RL is gone. RL plus RY is left, that's what it is. Okay? Now, if I wanted to find VL, all I have to do is to follow the Ohm law. VL says this is equal to RL IL. Okay, so this is going to be RL RY divided by RL plus RY times IY, capital IY. Okay. I want this VL to be the same as this VL, or I want this IL to be the same as this IL. Let's see what the conditions are. So let's put them together. This one, let me use a different color. It's going to be RL divided by RL plus RX times EX is equal to RL RY divided by RL plus RY times IY. Okay. Okay. Before I go ahead and analyze what we just got, I want to backtrack a bit of a step and see what happens in these two scenarios. This one, if RL is 0, what happens to my VL? If RL is 0, regardless of what IL is, VL is supposed to be 0. If RL is 0, that's going to be a short line, and it's going to give me IL. IL would be EX divided by RX. This one is a short line, EX is going to see RX in front of itself. If RL is 0, this is a complete short line. People come in, they see resistance, and they see no resistance to get to the same destination, and therefore when they come in, they prefer everybody to go to the no resistance at all. So all the IX are actually going to go through the short, if RL is equal to 0. In one sense, you can say that this IL for RL0 and this IL for RL0 should be the same. So if this is going to give you IY when RL is 0, is going to be, this is a short, EX divided by RX, obviously when RL is equal to 0 for this one. Let's try this one more time. If RL is infinity, that is going to give me an open line. This RL is infinity, that's going to be an open line. Let's see if these two are going to be behaving the same when RL is open. Now for RL open, IL is 0. Because IL is 0, there is no voltage drop across this. Therefore, EX actually drops itself on this one. This is going to be EX if RL is equal to infinity. And when this is open, nothing can go through this line. All the current goes through RY, hits the head of RY on top, creates a plus polarity and a minus polarity at the bottom. And therefore, this one is going to be IY RY. For this, provided that RL is equal to infinity. These two relationships have to give us some indications. EX is equal to RX IY. Let's take a look. EX is equal to RX IY. EX is equal to RY IY. It's very easy to see EX and EX are the same, IY and IY are the same, therefore RX and RY should be the same. Conclusion, RX has to be the same as RY. Okay? If I want to move from this structure to this structure, all I have to do is Rx has to be the same as Ry. I simply copy and paste it. If I want to go from here to here, I simply copy this resistor and paste it. That resistor is easily basically managed. The question is this: if I have Ex, do I have Iy? Yes. If you have Ex, Iy is going to be Ex divided by Rx. Ex divided by Rx is going to be Iy. If you have Iy, do I have Ex? If you have Iy, Iy is going to be my Ex. I can move from this topology to this, copy and paste the resistors, make sure they are the same, and this divided by this, that's the current, when the short happens, is going to be my Iy. This times this resistor when it's open is going to be the same as Ex when it's open. That's going to give me some rules and regulations to transform one side to another. You can actually go and find this simple understanding out of these relationships. You can basically get rid of the RL and inverse them and simplify them, and you're going to get to the same scenario you just talked about. The entire idea is this: I want to have a simple topology of a series voltage resistance into parallel current resistance without actually changing anything at the outside. Let's try this one more time, and I want you to basically feel the way it's going to be. Why do we do the source transformation? Let's take a look why we do the source transformation. One more time to show this graphically. If I want to find Iy, I know, let me erase this. Graphically would be better for us. If I have this and I want to find this, I copy the resistor. This current is going to go all the way through this short. If this is short, let me force this as short. This current goes all the way through this short and come back. This is going to be IY. This voltage and this resistor is going to give me IL. This EX and RX is going to be, I follow the mesh loop, if you want to, mesh equation or KVL equation, and I can easily find that. EX is now applied itself across the RX. The direction of the current is actually going to go this way. I need to make sure I choose a direction for IY that goes the same way. I'm looking at this in order to identify this direction. I'm looking at this one. If this is going to give me current to go through this one is going to give me current to go through this. So I have to make sure the direction is properly set. Resistors are no challenge. Suppose you have this topology and you want to go from this topology to that topology. Okay? It's easy. You copy the resistor. You are going to have this in your mind. This is completely broken open. When this is completely broken and open, the current comes in. The current comes in, hits the resistor RY at the top, creating plus polarity and minus polarity. The voltage across this is going to be IY RY. This is going to be IY RY. In terms of polarity, I'm going to mimic the same polarity I see. If this is plus minus, I'm going to see plus. If this is minus plus, I'm going to see minus plus. I'm going to go ahead and show you what we mean by source transformation and how it's going to help us. Let's take a look at the following example. Again, here is another chance for you to play a game, to devise a plan, to play a chess if you want. You need to see what is your future step. I have 3 amp, 2, 8, 3, okay. And the voltage of interest, or the point of interest, variable of interest, is the voltage across the 8 ohm. We have learned so many different techniques to solve this. In chapter 2, we would be writing the component law, the KCL law, the KVL law, a very extensive and expensive approach to solve the design. In chapter 3, we could do nodal equations and solve that, or supernode. We could do mesh and solve that, or supermesh. In chapter 4 beginning, we could do superpositions because you have two sources. You can shut down this and find the contribution of this across, or shut down this and find the contribution of this one across. A current source set to 0 is open, voltage source set to 0 is short. So these are different techniques. We are simply considering the circuit, analyzing the circuit in a different light. This time, it's source transformation. Why do I want to do source transformation? You see, right now, I can't see myself. Are these in series? No. Are these in parallel? No. These two are in parallel, of course. These two are in series, yes. If you identify a voltage source and a resistor in series, that's your library for source transformation. If you identify a current source and a resistor in parallel, that's your library. That's the one you are going to attack. So in this case, I'm going to go in and say, if I take this section in my mind, just imagine this separately here. You don't have to do this all the time. Just for the sake of clarity, I want you to take it down for now and draw this as a separate circuit for now. 3 amp. This is A and this is B, the two terminals. My load is going to be whatever you see under my hand. This is my load. This load is actually working up on this circuit under observation. I want to have the same behavior out of this when I look here. Regardless of what my RL is. RL is 0, RL is infinity. That's what I'm going to do. I'm going to take this and replace it with a voltage source and a resistor in series. Why do I want to do that? If I replace this one with a voltage source and a resistor in series, and if I take this and replace it here, if I replace it, you can see this resistor and this resistor. Do you see that? These two would be in series now. Now the collapsing this circuit would be possible for me to do. Through the transformation of this circuit topology, I can actually see these two in series. The same thing is true, I want you to go in more ahead of us. If you have 3 ohm and 12 volts in series, you have the library, and you can replace it with a current source and a resistor. Why do you want to do that? I didn't put the direction because we have to define that direction in a moment. And I didn't put the polarity as well. We need to find the polarity in a moment. Why do I want to do this? Because if I take this part and replace it by this, now I can see this and this are in parallel. They weren't in parallel or in series before. I'm massaging the topology as long as it doesn't hurt. I'm massaging the topology. And all I'm trying to do is to find this voltage. I'm changing this topology, maintaining external behavior. I'm changing this topology, maintaining external behavior. If the external behaviors are the same, I'm allowed to change that. The internal is going to be different. One of the mistakes I see in the exam is this. Is this current the same as this current? No. It's changed. The topology is changed in this sense. Inside, you can't say anything. Inside, things are going to be different. Topology is changing, but is this voltage the same as this? No, of course not. As soon as you change the topology, things are different. But this topology is going to help me. All I care is this. External behavior is going to be the same. How do I find this? It's easy. If you have 4 ohm, you just simply go in and you copy and paste. Right? Now, I want you to imagine the next stage. I want you to imagine that this is open in your mind. This current come in, and this current has no way to go. This is open, right? This current come in, and this current comes in and actually hits the 4 ohm at the bottom and moves through the 4 ohm. And if, as it does, it's going to actually create a voltage, plus and minus. That's your polarity. Plus, plus, minus, minus. How much is it? 3 amp, 4 ohm, 3 amp times 4 ohm, that's going to be 12 volts. So what am I trying to do? I'm actually trying to remove this part and replace it with this one. I'm going to replace it in red so you can see the change. That's 4 ohm. And this one is going to be plus minus 12 volts. This process has to be done relatively fast. Actually, source transformation is one of the easiest techniques in the 4 technique from the 4 techniques we have discussed so far. What do I see now? Why did I do this? I did this because I wanted to have 4 and 2 to be in series. Now that they are in series, I'm allowed to sum them up. They are in series, so I'm going to change that. This 4 and 2 is going to be 6. I'm going to have this. It's 4 plus 2 as equal to 6 ohm. Now I'm stuck. Is 6 ohm in parallel with 8 ohm? No. Are they in series? No. But I'm happy to report that there is a 12 volts and a 6 ohm in series. And that's my library. And I can take this and replace it with the new structure. I'm going to replace this with the new structure. In your mind, this is what you're going to see, separately, individually, in front of you. This is what you're seeing. Okay? I want to replace that with a current source and a resistor. No challenge in terms of resistor. The resistor is going to be 6 ohm. It's copy and pasted. Now what is the current? In order to find that current, I need you to, in your mind, not on the design, in your mind, I want you to put a short in front of it. And when you put a short in front of it, tell me what is the direction of the current and how much is that value is. Now, if you take a look at this, this is a plus. Through the plus, I'm going to have the current. The current is actually going this way. If I had happened to have the same short, I need to have this current to match. If this is a short, the only current that goes like this in a circle would be to go down. That's my direction. This doesn't exist. It's just here to actually help me to analyze my stuff. How much is the current? Obviously you have a voltage and it falls across a 6 ohm and you have a ohm law. So this is 12 divided by 6. That's going to be 2 amp. So this one is going to be 12 divided by 6 and 2 amp. So far so good? Now I want to remove this. Let's remove that and replace it with the new structure we found. Please note, this voltage is not the same as this anymore. This current is not the same as this current anymore. This topology has changed. But I don't care because it's internal. I want this. This is my own point of observation. I want this to be the same. So I'm going to remove this. And this segment that I have actually played with this one. This is going to be 6. That's going to be a current source, 2 amp. Okay? Okay. Now I'm in a better shape now. If you take a look at this, you can see 6 and 8 are in parallel and they are in parallel with 2 amp. Of course, you can say these voltages are the same. But you still have a bit of a challenge here. This is not helping, it's not friendly. This segment does not help me to shrink, compress the design. So what I'm going to do, I'm going to replace this section. I need you to extract this section in your mind. Just extract it for now. So let's have these 3 ohm and this plus minus 12 volts in front of you. The question is, how much is this resistor? It's very easy. This one is 3 ohm. I want to identify the current. In order to identify the current, I'm going to short this. The question is, this is all done in my mind, not on the actual design. The question is, which direction the current go? Plus goes like this. That's the way it goes. So this is the direction it goes. If I had this as a short, I want to have the same direction as I do have here. Therefore, because short in front of the 3 ohm is actually going to be short anyway, 0 ohm in parallel with any resistor is going to be 0. I have to assign this. The people come in, they see short resistance, no resistance, and 3 ohm resistance to the same place to get to the same destination, and therefore everybody goes through this. So that's going to be my direction. How much is the value? You have 12 volts and all falls across the 3 ohm. So this is going to be 12 divided by 3 and that's going to be 4 amp. Let's do that. Let's replace this with the structure you found. Are things different? This voltage and this voltage, yes. The current is going to be this different as soon as you load it. So it's going to be a new design, 3 ohm, and 4 amp. the entire game is played because I couldn't do shrinking and things weren't parallel series. By source transformation, I was able to transform a voltage source to a current source if I had voltage and a resistor in series, or a current source to a voltage source if I had a current source and a voltage and a resistor in parallel. So I utilize that kind of a knowledge to actually do the transformation. Take a look at this now. It's really nice. Parallel, everybody is meeting on one node on top and one node at the bottom. Everybody meets. Everybody is meeting now. Okay? I want to solve this. You have two current sources. Another lesson we would like to learn at this stage is this. As soon as you have two current sources in parallel, and we did talk about that in chapter 1 actually, just to refresh your memory. First of all, are these two in parallel? Yes. This current source and this current source are actually meeting on the top and they are meeting at the bottom. You need to make sure the two current sources are in parallel. If you do that, then I want you to actually temporarily imagine you're sitting on this node. On this node, $4 is coming to your pocket. $2 is leaving your pocket. How much is coming to your pocket? 2. How did you find it? You said 4 is coming and 2 is leaving. So I'm going to actually replace that. You said 4 is coming and 2 is leaving, right? So I'm going to, let me actually mimic the same structure. 4 and 2, opposite direction, only 2 is left. And this is only true if you have them in parallel. I need to alert you one more time, the two current sources must be in parallel. Now, what is the voltage of interest? The voltage of interest is VO. I have 3 resistors in parallel, and I can utilize the G rule. 1/8 divided by 1/8 plus 1/6 plus 1/3 times 2 amp is going to be I/O. Let's calculate that. So 1 divided by 8 divided by, open bracket, 1 divided by 8 plus 1 divided by 6 plus 1 divided by 3, close bracket. Then I'm going to time it by 2. It's going to be 0.4 amp. 0.4 amp. How much is my VO? My VO is 0.4 amp times 8. It's going to be 3.2 volts. I'm done it. This is a source transformation. Please remember though, not all the time source transformation is a possibility. You need to make sure that you have a voltage and a current in series. A voltage and a resistor in series, and a current and a resistor in parallel. You need to identify those blocks. If those blocks don't exist, you can't reform them. So that's one thing. Let me do one more, and then I'm going to close the topic of the source transformation. And then I'm going to go into the Thevenin and Norton scenario. Let's take a look. Okay. This is practice problem 4.6, and it's page 135. Okay. Relatively complex in one sense. Okay, I hope I have all the components. The resistors are all in ohm, the current sources are all in amp, the voltage is in volt, and my point of interest is the current of the 7 ohm. Well, in the exams, this circuit course is different in nature from many other courses you might have seen. We simply basically go and pick up one circuit topology, massage the numbers, change it, and put one resistor, perhaps in the middle. And as soon as we do that, the entire challenge is going to be different. Sometimes elements that are in series will no longer be in series, and parallel also, and that's going to give you challenges in terms of solving it. While on one end, I'm going to say that you have seen the circuit topologies when you come to midterm on the final. On another end, I'm going to advise you that we are going to make simple, small modifications that's going to make it a bit challenging in one sense. So what do you need to do? Sometime we get to the point when we say we know what the topic is, and we stop there. That's the biggest mistake you can do. The idea is to pick up the pen and paper and do all the way to the end and actually say, this is my number. If you do this a number of times, perhaps 10, 20 times for the midterm, then you might be safe, you might be good. But if you say, okay, I know what the equations are and I know how to solve that, that's going to be the most pitfall you're going to have in this class. I need you to, on the table, on the whiteboard, we might simply do that. We might simply say, these are the equations, this is how it's done, because we don't have time to solve it. But you need to go ahead to the very end and solve this. Okay, what do I have? I can do mesh, and I have a super mesh. If this is ground, I do have a super node. You have 3 sources, you can do superposition. A very good candidate for a midterm exam, very good candidate. So we might be giving you this and asking you to solve this super mesh, super node, superposition, and then source transformation. That's the type of a question you might be expecting in the midterm. Now, what's your game plan? This is your point of interest. And you need to tell me how you can actually, nothing else matters. Everything else, aside from this resistor, really doesn't matter to me. However you shrink this, it's up to you. So I want you to devise a plan. I have 1 and 4 in series, that's going to give me 5. I'm happy. 5 and 3 in parallel, 3 and this in parallel. I'm happy so far. This one, 6 and 3 are in parallel, and then I have a current source. But then I have a voltage source which is bugging me, and that voltage source does not let me talk to the 7 ohm in peace. So what I'm going to do, as soon as I have 3 and 6 in parallel and combined to one resistor, I'm going to change that to a voltage source and a resistor. Then I'm going to combine the voltage sources. Then I'm going to shrink this. Then I'm going to take it one more step to the current source and a resistor. Then everything looks like in parallel. So I need to have a plan in mind, and that plan is going to save you a lot of time. So 3 ohm and 6 ohm, only for 2 resistors. 3 times 6 divided by 3 plus 6 is going to be 2 ohm. So I'm going to say this one is in parallel with this one, and I'm going to replace it with one resistor, which is 2 ohm. Now you can see my challenge. There is nothing I can do with these guys. I have to do a transformation on this side. So I'm going to have a voltage source. What is the polarity? I don't know. I'm going to have a resistor. The resistor value is very fast to find. It's 2 ohm. But I want you to think of this in an isolated environment. Don't look at the circuit. If this current is open, if this node, these 2 nodes are open, the current comes in, the current goes in, hits the 2 ohm on top, and moves on. It's going to create a plus on top, and a minus at the bottom. This plus is going to come in, and it's going to be plus. This minus is going to come in, and it's going to be minus. That's the way I see it. Now, how much is the voltage? 5 amp comes in, hits the 2 amp, 5 amp times 2 ohm, this is going to be 10 volts. So this one is going to be 10 volts. I can say I can replace this with this structure in mind. So let's do that. I'm going to go ahead, replace it with a voltage source, 10 volts and 2 ohm. My gain is paying off. Why? Because I can see these components are in series. These components are in series. Can I shrink them further? Yes. If the resistors were in series, you would have added them up. Let me see what I can do. Take a look at this. This is 2 ohm. This is plus minus 5 volts. For a moment, I want you to actually look at this in an isolated environment. Okay? Now here is my node A and here is my node B. I need you to actually do me a favor and do a KVL law for me. This is plus, this is minus. Let's start from here. It's going to be minus VAB because I hit the minus polarity first. Of course, the current is 0 because I left it open, but there is a voltage and I want to find that voltage. This current is 0, okay, because it's open in my mind. AB are open. Then minus VAB plus 5 volts plus 2 times 0 amp is only in my mind plus 10 volts as equal to 0. How much is my VAB? My VAB is going to be, take it to the other end, this is 0, 5 and 10 is going to be 15 volts. It's very easy to see it. Take a look. This is me. That's 10 volts is my height. This is my son. That's the 5 volts is his height. I'm standing on the ground and I have my son on my shoulder. I'm 10 volt and he is 5 volts, so we are together 15 volts. That would be the height. Hypothetically talking about it, right? So you can see that if you look at it this way, you have plus 5, then you have plus 10. Let's go and make it difficult. If this is like this, what happens? Plus 5 minus 10. So you have minus 5. So you can actually see how this is coming from. The original form, let's go back. The original form was plus minus. You have plus, you sum them up. 5 plus 10 is 15. You can also extract the design, have it open, write at an I as equal to 0, and we are going to do that a number of times, and then get the shape in front of it, right? So let's see. I'm going to remove this. The 2 ohm, of course, is going to remain. This one is going to be plus minus 15 volts. Okay. I'm still in trouble because I intended to have everything in parallel and I don't. So I want to have everything in parallel. Let's take a look. What is my next move? What's my next move? Well, I have a voltage source and I have a resistor in series, and if I take this and make it a current source and a resistor in parallel, then I'm going to have many of the elements in parallel. I'm going to take this in mind and replace it with a current source and a resistor. The resistor is easy, that's 2 ohm. Right? Let me extract this design in my mind just for the sake of the simplicity. 15 volts and 2 ohm. This is the design and I want to transform it to this form. If I make this short, and if I make this short, what's the direction of my current? This is plus, the current goes like this. It goes like this. So I need to make sure I choose a direction for this current. When it goes through the wire, I'm going to actually see the same output current direction as I see in this one. The only direction that can satisfy this is going to be going up. Now how much is the value of the current in this loop? 15 falls across the 2 ohm. You can write a KVL if you like. It's going to be 15 divided by 2. It's going to give me 7.5 amp. So I'm going to go ahead and replace this part with a resistor and a current source. This is going to be 15 divided by 2, which is 7.5 amp, and this is going to be 2 ohm. Right? So now I'm a lot closer to my ultimate goal, and my ultimate goal was to have everything in parallel. 1 and 4 are in series, so I can actually remove that, and I'm going to replace it with 5. Okay? I see everything in parallel. The only challenge is, how do I see these two current sources? If there was an element in between, I wouldn't be able to count them as parallel. But since there is no component on top and no component at the bottom, these two actually see each other head to head and toe to toe. I see a common mistake, and that is, if you happen to have a resistor here, are they still in parallel? No, they are not. You can't even have your hands, because as soon as you get to this piece of a Lego, your hand is going to feel the pain. You can't go through the Lego. So this is going to be one line. In this scenario, this is going to be one line. That's why I'm going to count 3 and 7.5 as parallel. As soon as I say they are in parallel, I'm going to sit on this. $3 is coming to my pocket, $7.50 is coming to my pocket. It's going to be $10.50 coming to my pocket. So I'm going to replace that, this and this, with one current source, 3 plus 7.5 amp. It's going to be 2. It's going to be 7. Point of interest IO, and then 5. As you can see, I have been trying to explain these steps, and that's why it is taking so long for me to solve. But for you, young, energetic, intelligent people, it's going to be rather about 10 minutes. This is one of the questions that's going to be solved rather fast. So please exercise on this. That's going to put you in a very good mood as soon as you get the same response. So what do I see? I want IO. And IO is, I'm going to follow the G rule. 1/2 plus 1/5 times 7.5 amp. Now, of course, you go ahead and you calculate this. Let me calculate this, and then we go to the next topic. So 1 divided by 7 divided by open bracket, 1 divided by 7 plus 1 divided by 2 plus 1 divided by 5. Please utilize the brackets, times 7.5. You got 1.27. 1.27 amp. And the book answer might be off, or perhaps we might have made a mistake somewhere. Basically, I'm going to use the G rule. If you remember this is 7.5 plus 3 amp. That's going to be 10.5. That's going to be 10.5. And this one is going to give us the answer we are looking for. Let's calculate this. 1 divided by 7 divided by, please utilize the brackets, because often without the brackets we are going to be in difficult positions, times 10.5, we get 1.78. 1.78, and that's what the textbook has already given us. The answer is there, 1.78. But at the same time, there might be some mistakes in the answers of the textbook, any textbook. It's wise to check with the solutions we post on the Blackboard or on the internet. We may make mistakes because the environment sometimes is different. When we put it on the whiteboard, it's a different scenario, it's a lengthy scenario, but the expectation is known for midterm, and everybody is going to be performing the best in the midterm. Thank you.